Um, should be ready to go in a few seconds.
Yep, I see it on YouTube. Okay, I'll just pause it so that I don't go cross-eyed on the other screen. Okay, I think that's us. Okay, welcome everyone to the John Brown Memorial Lecture for 2021. Welcome to our guests that are attending via YouTube and also to our members who are here on Zoom. We have a very special guest tonight, Dr. Margaret Brown, who was married to the late John Brown. And it's very much appreciated that you could join us tonight, Margaret. Thank you for coming.
Pleasure, thank you.
Now, for those of you that don't know John, well, he's John Brown, OBE, Regius Professor of Astronomy, Astronomer Royal for Scotland, and amongst many other things, he was honorary president of this society. And he was also my mentor and a friend of mine. Now, in the spirit that John certainly instilled in me, if you have questions tonight and you're sitting there thinking, I don't understand that, I'd like to ask about that, but probably it's a silly question and everyone else knows the answer. Stop yourself and ask the questions. You can put it in the chat or you can ask if you're on Zoom in person at the end. Questions are very welcome and it'll be very much in the spirit of the John Brown Memorial Lecture. Now, tonight we're going to hear a talk about magnetic fields. And of course, John Brown's main research was on solar flares activity, and that centres around magnetic fields. And indeed, the work that I did with them in my PhD was looking at how solar activity in the magnetic fields of the sun and those virtual tentacles reached out through the solar system and really affected, well, it's one of the few branches of astronomy where it can affect what's going on here on Earth. It can bring, solar activity can bring down satellites early. It can overload power systems, cause power lines to shut down, which happened in Quebec about 30 years ago. And in some serious cases, it's even rumoured that it took repeats of Star Trek off the telly when a satellite got damaged. So these are important matters, I'm sure you'll understand. Now, actually, when I started my PhD, the other connection that tonight's lecturer is that when I started my PhD, one of the first things we did is that John Brown set up a meeting with a couple of folk who came over from Edinburgh from the British Geological Survey, so we could talk to them about the Earth's magnetic field, which we didn't know quite so much about. So it's, I think, quite appropriate tonight that we are being visited again by a senior geophysicist from the British Geological Survey over in Edinburgh. And I would like to welcome Dr. Ciaran Beggan, who's going to talk to us about a tour of solar magnetic fields in our solar system. Ciaran, over to you.
Thank you very much. And I'm delighted to be talking to the Geological Society of Glasgow. I'll just share my screen and then we can kick off the presentation. So I'm hoping you can all see that in full screen mode. Is that correct?
Yes, looking good.
Excellent. Okay, well, thank you very much. Okay, so I'll get started. So the kind of topic was, I suppose, where would my compass point? And thinking about where would your compass point if you were to take it on a tour of the planets of the solar system, and what we've learned in the kind of the last 30 or 40 years that somebody, say, a century ago wouldn't have known about. I'm a senior geophysicist at the British Geological Survey in the Edinburgh office, where the geomagnetism team is based. And most of the work I do is on Planetary, planet Earth, and the geomagnetic field. So this is kind of a little bit outside my area of research, but certainly not outside my area of interest. So without further ado, I'll just say that if we were talking 100 years ago and we're looking at the planets in the sky, we wouldn't have known whether magnetic fields existed on any of the other planets. The sun itself was kind of known to be a magnetic body because of, as mentioned, solar storms and the impact of the aurora. And that was just about understood at the time. But we now know, thanks to 50 years of solar system exploration, that magnetic fields are ubiquitous in the solar system. And here's a nice picture of the aurora in Iceland somewhere. And you can see that's a direct interaction of the Earth and the sun's magnetic field, essentially. So if you study the magnetic field, well, what does it tell you about? It's a very simple geophysical property to study in some sense. And if you see a planet that has a magnetic field, you can tell something about the composition of the planet, its depth, and it's possibly something to do with its temperature in its core or its mantle. If it's got a magnetic field in its crust or its upper part of its mantle, tells something about the composition, the depth of that crust, and possibly the history. As you can see, something like paleomagnetic remnant fields. It's got an ionosphere and atmosphere. You can tell the composition from the types of ions that you might see. And here you've got a nice green glow. It indicates nitrogen, or if it's red, it's oxygen, for example. And then more importantly, most spacecraft don't fly that close to the surface. So they typically fly to the space environment, the radiation belts or Van Allen belts as they're called, or where trapped particles from the solar wind are captured. And you've also got the magnetospheric influence of moons and vice versa, the influence of moons in the magnetosphere. So it's got lots of applications. In fact, one of the kind of first applications of magnetic field in sort of space exploration was to work out what the rotation rate of Jupiter and Saturn were, to kind of more precisely, particularly Saturn, because it's not further away and kind of difficult to see features on it. Obviously on Earth, we use it for navigation. That's the first purpose of the magnetic field. But Mars has what looks like possibly plate tectonics, if you look at its magnetic field trapped in the rocks on the surface. And it can also use to probe the various planets for the depth of the source, the depth of the core. So for example, in Mercury or in the ice giants or the gas giants. And finally, where you find things like salty water, you can detect an induced magnetic field. And so if you're looking at the moons of Jupiter, for example, that's another use of the magnetic field, where you see it disturbed as you fly over the planetary body of the moon in question. So yeah, let's have a quick tour. So here are the planets, a couple of moons, and then off to the right-hand side, you'd expect Pluto as a dwarf planet. So which of these have magnetic fields? Well, we know now that most of them do, including Mercury, and then the ice giants as well, and some of the moons. But surprisingly, Venus doesn't have a magnetic field, and it looks like Mars did, but it's long dead. Why does Mars not have a field when somewhere like Mercury does, despite being smaller? And Pluto didn't have a magnetic field detected as it went past. Doesn't mean there isn't one, but it seems unlikely, given the closeness that the New Horizons probe went past it. But it might still have a small magnetic field. Okay, so let's go through the kind of the yeses in kind of a fairly whistle-stop tour to kind of get through all the kind of what are the latest thinking and latest kind of findings in these bodies. So we'll start with one that I know and love best, which is the Earth. But first of all, I wanted to kind of give you a quick idea of the relative sizes of the magnetospheres, of the kind of the influence in space of these particular planets. And so we've got this nice picture from Fran Beggan and Steve Bartlett, or Bartlett rather, you can find on the web. So here's the sort of magnetic field of Mercury, which is closest into the sun. And it's about 12,000 kilometers across in this image. But that in itself is actually quite small, and it would sort of more or less comfortably fit inside the diameter of the Earth. And you can see there the Earth is much bigger, and it protrudes a lot further out into space, and its magnetic bubble is just bigger. For two reasons: the field is stronger and it's further away from the sun, so the solar wind is relatively weaker at this point. If you move out further away, look at somewhere like Saturn, that's got a bigger magnetic field again. And the Earth's magnetic field now more or less fit, with that box anyway, within the kind of diameter of Saturn. And again, you can see Saturn's got a much bigger field than the Earth. And again, that's because it's much, much further away. And then you come to the giant of the solar system, which is Jupiter. That's got an enormous magnetosphere and magnetic field. It's got a very, very strong magnetic field, very, very strong dynamo, very energetic body. And so it generates a very large magnetic field. So we'll talk about that later on. But just kind of give you a relative sense of the size of these things. The one in Mercury is tiny, and the one in Jupiter is absolutely enormous. So let's start with Earth, everyone's favorite planet. We all live here. So it's called this a classic planetary field, because it's where we sort of learned about what a magnetic field is and how it is created. So first of all, here's a few vital statistics for each planet as we go through, and just give you a feel of the various sizes. So here's an image on the right from the European Space Agency, one of their kind of body bits of department, I suppose, that creates these nice images. And it's the Earth's magnetic field sort of visualized sitting in space, and it's impinged on one side by the solar wind, which depresses it on the sunlit side, and it's stretched out into a tail on dark side. And you can see that sort of where the field pops out, sort of offset from the rotation axis slightly, and you can see that kind of like transparent mantle and the inner and the outer core mark there. And this is not just a kind of fixed picture, it's a sort of dynamic picture. It's a very sort of fluctuates rapidly in hours, seconds, minutes, and over 11 years with the solar cycle. So the Earth is kind of pretty much a round body, more or less. It's very slightly flattened, and of course we all know it rotates once a day, which is good for us. So the field is kind of like more or less aligned along the rotation axis. It's about 10 degrees offset at the moment. It's not particularly strong magnetic fields, and its surface is measured, field is between 23 and sort of 65,000 nanotesla. And then nanotesla is a very small unit of magnetic field strength, if you want to think about it that way. And your average fridge magnet will probably be 10 to 100 times stronger than the Earth's magnetic field. And we know from geophysical investigation over the last 100 years that the magnetic field is generated in the outer core, which is roughly about halfway to the center of the Earth. And then the magnetosphere extends about 6 Earth radii out to the front and about 100 out on the back. And occasionally the moon does pass through the magnetotail of the Earth, and probably around about this time, typically on the full moon nights as we see it. Okay, so obviously magnetism is kind of its main priority historically has been for navigation, and I'm sure we've all got a compass that we've used at some point. And I've shown a sort of an old ship's compass there. That's kind of what we all think about with magnetism. And there's a nice picture there of the RSS Discovery, that was Scott's ship on his research trip to the Antarctic in the turn of the last century. So just to kind of point out that compass does approximately point north, but I'll refer to this occasionally throughout it, but you've got to remember that you can approximate the Earth's magnetic field as a bar magnet. So if you imagine a sort of fixed bar magnet inside the Earth, but remember, by convention, your compass points to the North Pole because people who invented the science live in the Northern Hemisphere, so it's the natural way of thinking about it. But of course, your compass's north part of the needle points towards the Earth's south pole. So the North Magnetic Pole is actually the south pole of the Earth's magnetic field. So think about it that way. And I just wanted to point out, hopefully you can see my mouse. So the lines here in the Northern Hemisphere point into the ground. Although we do say that the angle is positive, the vertical angle is positive in the Northern Hemisphere, negative in the Southern Hemisphere. If you think about the field lines themselves, they point outwards in the Southern Hemisphere and they point inwards in the Northern Hemisphere. So we'll come back to that as we look at other planets' magnetic fields. Okay, so one of the things we do at BGS in Edinburgh is we make observations at observatories. There's 3 in the UK at the moment. And Britain has a long history of magnetic field observations, starting in London in the 1840s in the Greenwich Observatory at the time. And of course, it was part of the Admiralty for safe navigation at sea. And here's a nice picture. I always quite like this from a magazine of the Abinger Observatory, which is the Greenwich Observatory was moved out of London when the trains were electrified. It was disturbing the magnetic field too much. And so here you see everybody in nice suits, all the scientists lining up, making measurements, and the technicians changing paper on the kind of rolls of photographic paper they use to measure the field. Nowadays, that's all digital, of course. So we've got 3 observatories in the UK that are all fully digital, and they measure using digital compasses, essentially, the magnetic variation. And here's a typical plot over a day from Heartland in Devon. You've got declination, which is the angle between true north and magnetic north. It varies about 1/10 of a degree or so over a day. And it's at the moment, it's minus 1.2 degrees pointing west, so west of true north. Then you've got the horizontal intensity and the vertical intensity. Again, you can see they vary by maybe 10 or 20 nanoteslas per day on a quiet day. They get much larger on a more geomagnetically active day when there's a solar storm, but that's an entirely different talk. So as you might have heard over the years, magnetic poles are not fixed either, and the magnetic field of the Earth actually changes quite a lot. So in the Northern Hemisphere between 1900 and 2025, the magnetic field has actually moved around about 2,500 kilometers. But in the Southern Hemisphere, it's just moved about half that, about 1,500 kilometers or 1,200 kilometers, and it's now sort of sitting slightly offshore of Antarctica. Those are the dipoles where the magnetic field goes vertically into the ground. But there's another kind of more average, sort of the equivalent of the dipole position. That really hasn't moved very much at all. mean that most of the change from the Earth's magnetic field is not the dipole component or the baromagnetic component, but all the other bits that make up the field as well. And you can look at that another way. Here's just time along the bottom axis and velocity of the dipole over time, and this time the colors are just represent the north and south. And you can see that the North Pole really took off around about the 1980s, sped up a lot, and it's been around about 50 kilometers a year for the past 2 decades or so. It seems to be slowing back down again, but that just could be an artifact of the lack of data in the last few years. It takes a while for the observatories to kind of dish out the magnetic field data and for the models to catch up. Okay, so here's what a map of the Earth's magnetic field looks like. It's roughly dipolar, but it's not really. So the magnetic pole is over here in northern Canada, say, but actually there's a second sort of minor pole here over Siberia. There's where the magnetic pole in the south is, roughly over Western Antarctica. And then you've got this kind of low region in the middle of the Atlantic called the South Atlantic Anomaly. And that's a persistent low region that's been there for hundreds of years, possibly thousands. And the magnetic dip equator is this line where it says 0. So that's actually quite a complicated field. And if you're thinking about your compass, this is what the declination map looks like. You've got several different lines, but if you focus on the green line here, for example, if you stand on this green line indicated 0, then your compass will point directly to north. If you're standing in the blue zones, your compass is pointing west of north by these particular angles, and you're on the other side, you're pointing east of north. So although your compass points approximately north of the Earth, that's not actually true in very many places at all. So in order to accurately use a compass, you need a map, which is what the BGS provide, of the difference between true north and magnetic north, where you are in the world. And this is automatically embedded in your smartphone, for example, where people like Google or Apple will take these maps that we produce, embed them as software in your mobile phone. And when you open up the mapping application, the onboard compass will detect magnetic north and then automatically rotate your map towards true north. Okay, so if you want to explain the magnetic field, here's some kind of general characteristics. Where does it come from? So we find that most of it comes from inside the Earth, about 90% of it explained by the dipole part. It's not coincident with the rotation axis. It's very weak and it can only turn a small needle, and it drifts rather slowly at about 20 kilometers a year on average, although the North Pole has been moving at say 50. So it doesn't drift uniformly around the world. And we know from looking at rocks and volcanic rocks and so on in the oceans and so on that reversals of the field have taken place. So it's swapped polarity, and it does so randomly. So the original proposer of magnetic theory was a guy called Gilbert, who was Queen Elizabeth's first physician back in 1600. And he suggested it was a permanent magnet, but he didn't know at the time that the magnetic field changes its shape and position all the time. So we can rule that out. A permanent magnet would just not be able to reverse or wouldn't be able to move slowly with time, although it would explain some of the other aspects, of course. What if there were electric currents flowing around in the rocks? That would be another explanation. But rocks are not very electrically conductive, and if it really was the case that there were electric currents flowing around the rocks, you get an electric shock every time you touch the rock or touch the ground. So that is not borne by our experience or experiments, so that's out as well. About 50 years ago, the suggestion that it was to do with the rotation of the Earth. It was suggested that bodies that rotate faster have a larger magnetic field. But the prediction of that was that if you went deeper into the Earth, that the magnetic field would weaken as the rotation was smaller near the center of the Earth. But actually, it's the opposite. Those experiments were done in Edinburgh back in the 50s by Ken Carew and his colleagues. So that was misproven. So around the 1950s and 60s, this idea of what's called a big word, magnetohydrodynamic process in the fluid outer core was settled upon as probably being the most likely reason why we have a magnetic field as we do in the Earth. So I'll explain that quickly. So you think about the composition of the Earth, you've got the inner core, which is this solid ball of iron, about the size of the moon. So when you look at the moon, think of that as a solid ball of iron. I think that's right below your feet. Then you've got the outer liquid core, which is about the size of Mars. That's quite large as well. And we've got the rocky mantle, which is kind of less dense. Each of these layers is less dense than the one below it. So they all kind of that's why they tend to sit there. And then of course on top, you've got the crust, which is where we live. And you've got all the kind of dregs that the Earth doesn't like, such as water and air, which all get expelled out of the surface because of the lightest elements, molecules. So if you think about the center of the Earth, it's got this liquid outer core, and this is what generates the Earth's magnetic field about halfway to the center. So it's actually made of liquid iron and nickel mostly, and other stuff such as sulfur, oxygen, lithium, and all those kind of things. So it's very hot, even though it's under a lot of pressure. It's well over 3,000 Kelvin. And surprisingly, it's about as runny as water is on the surface. So if you look at my kind of glass of water or your beer or cup of tea or whatever you're drinking there, and think about that, that's about how runny liquid iron is in the center of the Earth, which is kind of not kind of what we would typically think of in terms of liquid iron. So it's very runny and it's very hot. And of course, the Earth rotates once per day, so it gives it a spin. It's got differential rotation. So if you are near the edge, you experience a difference force than if you're kind of near the inner core boundary. And also, as the inner core is solidifying, light elements are released as this solid iron compacts into a crystal. It releases any kind of impurities, let's say, and they get released off and they drift off from the bottom of the core to the top of the core. So they stir the core constantly. So you've got two sets of stirrings, rotation and buoyancy. So the fluid moves really easily, it's very conductive. And so what happens is there's an existing magnetic field that gets twisted up. When you twist the magnetic field in motion, you get an electric field. The electric field then creates a secondary magnetic field. And so what you have really is a very large current system running around the center of the Earth, roughly in an equatorial plane. And that generates the majority of the magnetic field. And so we can model this in the computer. And here's an early version from a guy called Gary Platzmeyer from the 1990s. This is a famous one. And what you can see is that if you can imagine the surface of the outer core is sort of roughly where the ball of spaghetti ends, and then you see the field lines poking out as kind of expected, the kind of like the dumbbell ears of the magnetic field. But inside, it's a tangled mess of magnetic fields all twisted in order to keep the geodynamo going. So what you're getting is geodynamo is basically heat converts to motion, converts to electricity, converts to magnetism. And overall, the geodynamo outputs about 60 gigawatts, which sounds like a lot, but it's basically about as much electricity as the UK is using at the moment. And it's about 1/1,000,000th of the power subtended on the Earth by the sun every second. So it's really a very, very small amount of energy in the grand scheme of things. Okay, so jumping on to the kind of other magnetic fields. So that with the Earth as background, let's look at other magnetic fields and see kind of in the context of the Earth how we explain these things. So unfortunately, the first one is Mercury, which is actually kind of unexplained and quite a mystery as to why it has a magnetic field. So remember, Mercury is quite a small planet, not much bigger than the moon. It rotates very slowly, about 58 days to do one rotation, and it's quite close to the sun, of course, and it has no atmosphere. So its magnetic field is actually very small tilt-off axis, about 5 degrees, and it's really weak. It's about 1/100th the strength of the Earth's magnetic field at the surface. It's got a very large core, about 80% of the planet is core, solid and liquid. And its field is asymmetric, as in it's sort of like, it's not centered, it's pushed to the north. So it sort of pops out the north a bit more than does the south. And of course, this magnetosphere is constantly battered by the solar wind. And so it's constantly altering. And so the solar wind variation at the surface can be something like 150 nanotesla, or roughly half the size of the main field, which is quite impressive. It was first discovered by Mariner in 1974, and when they first put together the Mariner mission, they didn't want to put a magnetometer on it. They were persuaded to by one of the scientists, and so they were stunned when they found that Mercury actually had a magnetic field. So there was a long gap before another mission went back 30 odd years. Nearly 40 actually, and finally the Messenger mission in the NASA mission was there about 4 years, and it went into orbit over Mercury, and it had a magnetometer and got really good measurements, which is most of what the talk is based upon in terms of the information available. And this year, a few months ago actually, Bepi Colombo, the European Space Agency mission, swung past on its first flyby. I think it does a few more next year, and then it will go into orbit in a couple of years' time, 2023. And I quite like this image on their Twitter feed because you can see the magnetometer sitting at the end of the boom there. I think it's about 10 or 12 meters long. So a really nice one, the magnetometer and Mercury in the background. Pretty cool. Now, the really weird thing about Mercury is it has no, well, you know, it has no atmosphere, so it has no ionosphere. And so it doesn't really have aurora in the same way that you do on Earth. So the aurora is basically the radiation belts connecting into the ionosphere, and it creates a kind of electrical circuit. And so when you see the aurora, what you're seeing basically is an electrical flow connecting the outer part of the magnetosphere to the inner part of the ionosphere and back out again. Because Mercury has no ionosphere, then they think that the currents flow directly into the core. So they basically pass straight to the mantle, the thin mantle, into the core, and then short circuit across the core, and then flow back out again from the magnetosphere. So actually, if you were on Mercury and you touch the ground, you might get an electric shock, actually, or certainly if you laid out a long cable, you'd probably, you might get free electricity, I suppose, actually, but certainly you could generate enough current to do some damage. And there's some suggestion between Mariner and Messenger that that the magnetic field of Mercury has changed over time, and in fact, it could even reverse. But the real mystery is such a small planet, how has the core stayed liquid for so long? Because it's still a substantially liquid core, and given it should have cooled, billions of years ago, no one's quite sure how this has been the case. So yeah, a mystery to be solved by Bepi Colombo. Let's hope. So yeah, can you take your compass to Mercury? You really can. It's a very small compass though, because it's not a very strong field. And I suspect it would point north most of the time, but during a big storm, it would probably wobble quite a lot, probably deviate quite a bit. Okay, so the next one is Jupiter, the kind of the beast of the magnetic fields in the solar system. And as you know, Jupiter is around about 70,000 kilometers, so about 10 times the diameter or the radius of Earth, whatever way you look at it, about 300 times more massive, although not quite as dense. And it rotates very fast, and it's obviously quite far away, about 5 AU from the sun. So Jupiter has this enormous magnetosphere, and it's full of dust and plasma, not from the solar wind, but from Io, which is that volcanic moon that ejects thousands of tons of dust and rubbish every day into the out of its atmosphere straight into space. So it all gets picked up by the magnetosphere of Mercury because it's charged. So, sorry, Jupiter, because it's charged. So Jupiter is kind of Earth-like in the sense that it's got about a dipole tilt of around about 10 degrees off its rotation axis, and its field is about 20 times stronger. But its field actually points in the opposite direction compared to Earth, so it's inverted in that sense. And it's got an enormous magnetosphere, as I keep saying. So what I quite like about this is that if we could see the magnetosphere of Jupiter, and of course Jupiter is visible in the skies at the moment, it would subtend about 1.5 degrees. So it would be like basically about 9 times the size of the full moon, which it would look amazing, wouldn't it? Well, I think it would anyway. So that's my favorite factoid about Jupiter's magnetosphere. And it was first discovered by radio telescopes back in the 50s. People realized if you pointed a radio telescope or a cone or whatever at Jupiter, you detect these kind of radio emissions in the Deca, the kilometric wave range. And it was the first time it allowed kind of the rotation to be estimated kind of very precisely, which was at about 9 hours, 55 minutes, give or take. It's been refined since obviously the missions of Voyager and Galileo went past. So the current mission is Juno, and this is a great mission. I read up about it. It's a fantastic piece of kit. And Juno is a NASA mission that's been there since 2015. And I quite like it. It's quite a cool looking shape as well, the kind of triangle thing. And the magnetometer sits out at the end, and it's a spin stabilized craft, so it spins every 30 seconds or so. And as it goes around Jupiter, it gets up to a massive 55 kilometers per second as it skims about 4% over Jupiter's surface, so a few thousand kilometers above the cloud tops. It's got 2 magnetometers on board on this 12-inch boom. The magnetometers have these CHUs, which are camera head units, and they basically stare at stars so they can orient the magnetic field measurements in three dimensions. And all magnetometers have that. And they've got 2, one inboard and one outboard. And the idea is that you can look at the difference between these two and sort of take out the noise from the solar panels and the electronics of the spacecraft, which will normally pollute your measurements. These kind of spacecraft, even 12 meters is not far enough away from solar panels. They're only about 2 meters away from solar panels, really, to get a good clean signal. Okay, as I said, Jupiter's got this very large radiation belt, and it's got very strong radiation belts as well. So if Juno was to pass through the radiation belts, it'd be fried within a few orbits. So intensively, particles, the ions and the electrons within that radiation belt, because they generate those big radio waves. So it basically kind of threads the needle and kind of pokes its way through these very narrow gaps between the radiation belts and the surface, and it passes through them very, very quickly as it can. And so it sort of like creates this sort of mesh around Jupiter as it passes over and goes through, which is really nice. And it's sort of designed to sample different longitudes as it goes through so that you can get a better picture of the magnetic field. So the thing about Jupiter is it's got a surprisingly non-dipolar field. So, a bit like the Earth, it's not a pure dipole. It's got these kind of like protrusions or strong patches that mean that a compass would not actually point completely north, depending where you are on Jupiter. And it's got this great blue spot, it's called on the equator, which is actually a strong patch, but when you plot it in a different way, it looks blue. So here's a kind of plot of all the orbits that went over, and amazingly or serendipitously, the first orbit they went over this blue spot, which kind of really confused them. But after subsequent orbits, they found that, well, it is actually an anomaly. There's another one up here, but the main part of the magnetic field has got around about 45 degrees north, and it got this large bulge. And then when you look at, it's got this dark line here, that's the trace of Io on the aurora, which I'll show in the next one, on the north and the south poles. So the field is believed to be created by electrical conductivity, so currents basically flowing around in a metallic hydrogen layer. And again, that forms a kind of ring of electric current inside the planet, which generates the kind of dipole part. But then there must be other localized regions where, for whatever reason, composition is different, and you get just a different electrical current. And it's roughly about 0.8 or so into the, about 0.85, I think the recent results show. So, and it also varies over time. It looks like it does evolve over time. And there's been some nice papers showing the difference between Voyager and Galileo and Juno in the last 40 years. So just one thing to point out is Io is just kind of like, it's the elephant in the room. If it wasn't for Io, it probably wouldn't have such a kind of amazing aurora. So Io basically pumps all this dust into the magnetosphere, and that creates these enormous ring dangerous currents in the ring belt, and it generates kind of tubes, flux tubes they're called, where electricity flows between the planets and the moons, all of them. And so they create, on the aurora, they create these like bright sparks where there's additional electrical current flowing into the atmosphere. And these images are Hubble images, these kind of nice blue ones you often see. They show the 3 closest planets with their flux tubes. And I was at a talk recently where someone was describing that actually there's X-ray aurora as well. So if you could see an X-ray, you'd also see the aurora on Jupiter, which I think is amazing. So a compass would generally point south over most of the globe, except for maybe these kind of little very, very strong patches. And of course, the bonus is you could use a very large needle. It might be kind of, maybe use a meter-long needle or something like that if you want to do. So that would be quite cool if you could float over the moon, over the surface of Jupiter. I just want to point out, Jupiter's got these icy moons, which are really, really interesting as well. And you've got Europa, which is about the size of the moon, and it's got an intrinsic field. And you've got Ganymede as well, which is the largest moon, and that's got an intrinsic field as well, roughly the same size as Mercury. And they think it's generated in an ocean around about 100 kilometers thick. So it's a target for a new mission called JUICE, or Jupiter Icy Moons, that the European Space Agency is launching in a couple of years' time. So that'll get there about 2030. So that's something to look forward to. It'll explore all these moons in more detail. But the thing about Ganymede is it actually produces its own little magnetosphere inside Jupiter's magnetosphere. So it's the first example we've ever seen of that. So I think it's quite good. So I think Ganymede deserves its own little tour. So if you brought your compass to Ganymede, it's got the same direction as the Earth. So you can see all the field lines are pointing in. And so your compasses work pretty much the same on Earth, actually, although again, a bit weaker, but probably behave much kind of more well or better than it would on Mercury, because there's not the same amount of buffering from the solar wind. Okay, Saturn, I think it's the most perfect and most boring planetary field, if you want to look at it that way. Again, it's as you know, it's smaller than Jupiter. It's got the rings and further out. It's got a 10-hour rotation period, similar to Jupiter, and it's actually very oblate, very flattened. But the interesting about Saturn is it's got the most aligned rotation and magnetic field anyone's ever seen. And so the dipole tilt is 0 to within some extraordinarily small number. So it's 1,000 times more symmetric than axisymmetric than Earth or Jupiter. And interestingly, it breaks this idea developed by a scientist called Cowling, who said that if your dipole and your rotation axis are aligned, then you can't have a magnetic field. So it's called Cowling's anti-dynamo theory. But it's obviously not true that Saturn's field is completely aligned, because otherwise it wouldn't exist. So the magnetosphere is, again, one of these very complicated ones, because it's so large. It's got all these dusty moons. spewing ions out into it. So you get, again, a kind of large, very active, although not quite as dangerous, ring currents and radiation belts and so on. And so you get very complex plasma flow across the magnetosphere, which is the kind of things that Cassini saw when they went there. And there's a lot of people in, say, the Imperial College or Lancaster who work on this particular problem. So here's Cassini. I think it's a brilliant craft, really, really cool looking craft. And you can see that the magnetometer again is sitting out the boom. It was built in the 90s by Imperial College, and they still build magnetometers for spacecraft. And here you can see, I've got a picture here, it's about 20 centimeters long, about the size of your hand. The actual magnetometer is this white thing here, and then you've got the shield that would go over top for keeping it cool. And then you've got this really nice retro circuit board that I presume was handmade by a technician in Imperial College. I really like that idea. Nowadays, of course, there's always a little boring computer chip doing something very exciting, but not quite as kind of tactile, I think, as these things. So the important thing about Cassini is that it was spin stabilized. So it always, basically, they were able to point it and it just stayed in the same direction. And I'll come back to why that's important later on. So just before it was crashed into the atmosphere of Saturn, it went through what they called the grand finale, where they did around about 10 or so passes. And this is just an image here showing, this is Saturn looking sort of towards the equator. So this would be the North Pole at top and the South Pole at the bottom. And they basically just, on this axis is just the distance away from Saturn. So obviously when the satellite came in, or the orbiter came in, it would actually, of course, go around the planets, but it came in at reasonably low latitude, so never really probed much beyond 60 degrees or so in terms of the absolute latitude. So of course it would have swung in and swung around again, would have looped around. But here they're just showing it as it passes in and out. You just see the rings kind of denoted there. So what did it see? And this is why we know the magnetic field is so boring. Here's the radial part of the point we're pointing out a bit. So over like roughly about 10 passes, each time it showed more or less the same thing. Here's the northward pointing part of the field, and again it shows the same thing. And then the only thing, kind of interesting bit, but you'll notice the scale is now 0 to 100 rather than 0 to sort of 20,000, is as it came through, it detected these little kind of dimples. These are the electric currents flowing to the field aligned currents. And these are these electric currents that flow between the moons and the ionosphere, or the upper atmosphere of Saturn. And then they think they detected what they called a small low latitude field aligned current, or aurora, at these latitudes, which are these little kind of bits here. They're not the main magnetic field because they don't overlap in time. They're always varying like all these other ones. So they think they're transient currents that are detected, which would be a first for a planet having such low latitude aurora. Okay, so Saturn, again, the composition and why does magnetic field is not really known. So there's a lot of modeling done on this and people kind of take a guess. This is the latest one I spotted this year from Sabine Stanley in NASA. And she's suggesting that that there's a layer about halfway to the center where the hydrogen becomes metallic like Jupiter, but it's inhibiting some of the formation of the kind of non-dipolar parts by this idea of helium rain. So that's kind of the latest theory, that the helium rain somehow makes it more perfect. But the magnetic field is not completely symmetric. It is 100 kilometers displaced away from the equator from a sort of perfect dipole. So it's slightly weaker in the north than the south. And actually there are these different hemispherical periodicities of the magnetic field. So it rotates, or it sort of pulses at slightly longer than the rotation period in the northern hemisphere and much longer in the southern hemisphere. Although, so it's got seasonal variations of this value, but we haven't detected any actual change in the field over 40 years. So it's interesting. And of course, Saturn has a nice aurora as well that you can see again from Hubble. It's also got this moon Enceladus with its induced magnetic field from what they think is an ocean. And they did 8 passes over Enceladus. And the last one, they got really low, down about 50 kilometers, I think, about 30 miles, right over the South Pole. And I saw a talk about this a couple of years ago, and the scientist was describing how the atmosphere was so dense, and of course Cassini wasn't designed to fly in a dense atmosphere, that the satellite started to wobble and tip, and they almost lost the satellite because it was about to tip over on one of its axes, and they couldn't recover from that kind of spin, because they didn't have enough fuel in the tanks essentially to kind of reorientate it. So we tumbled out of control and possibly crashed. So they didn't do that again. Okay, so if you went to Saturn, your compass would point exactly south everywhere, and you can bring your own compass because it's roughly Earth-like, so your compass on Earth would work there. Okay, so off to the kind of two least known about, Uranus. First of all, and this one is curious because it's the most offset in terms of its distance from the rotation axis. And of course, hopefully you know that Uranus is a bit odd anyway. It spins on its side, so its rotation axis is in the plane of the sun essentially. This is from Voyager when the South Pole was pointing more or less towards the sun. Over the last 30 years, or 40 years, 50 years, it's rotated so that it's in a different season now. So the South Pole is pointing kind of pointing back along the axis of the direction of the planet traveling along its orbit. So these are kind of ice giants, but again, no one's quite sure what their true composition is, and we've only had one flyby, and it's difficult to detect the actual detailed gravitational and sort of rotational body aspects that you need for Uranus and Neptune to say for sure. But yeah, here it is. So here's a nice diagram. So as Voyager 2 went past, the rotation axis, South Pole, was pointing more or less towards the sun, and the magnetic field axis is pointing around about 60 degrees off that. And the ring system is just shown here in these kind of like dotted dash, kind of like a bar going through it. So as you can imagine, as the planet spins, that magnetic field rotates a full axis all the way around. Because it's not aligned, you get the sort of a very strange kind of wobbling of the magnetic field around the rotation axis. Surface fields roughly Earth-like, and they think the source is kind of hydrogen ice, maybe. I'm not quite sure, water ice perhaps, roughly somewhat near the surface. The other thing to point out is that the pole, the magnetic field, is offset by roughly 1/3 of the radius. Its magnetosphere, because it's so far out away from the sun, actually extends out quite a bit. And the whole thing rotates in a kind of corkscrew pattern, and it leaves behind this kind of very odd magnetosphere wake behind it as the planet moves along its orbital path. I'll try and show you that next. Okay, so yeah, there's a brief contact by Voyager. I think it was only about 2 days. That was kind of close enough to make a kind of any reasonable measurements. It came in about 50,000 kilometers in around 1986. And so this is kind of the best guess, sort of upper atmosphere, kind of watery stuff, and maybe a mantle of ice and maybe a small core of rock, but that's only a guess. Think about Uranus, it's very cold. It's also in a retrograde orbit, so it seems to be that it was hit by something at some point in its life, and basically kind of knocked the stuffing out of it. But it still has a magnetic field. And again, why that is the case, it's not really sure where the energy comes from to drive a magnetic field. Not very clear. Rotation, I guess, but it rotates relatively slowly, I suppose. And yeah, so as I said, the field is highly inclined and offset. And it's actually, rather than the Earth or all the other planets which have one magnetic equator, this one's going to have 3 or probably more magnetic equators, if you were to make a full survey of it. And of course, very complex rotation in 3 dimensions. So I'll show you that. So this is kind of from 2017. So the blue arrow is the rotation axis, and you can see the magnetic field spinning around once per day, every now and then the moon goes past, and the yellow arrow just shows you the direction of the sun. So you can see the magnetic field kind of going around a bit like a kind of fairground ride. And of course, as the moon moves kind of perpendicular to the sun, it kind of leaves this corkscrew behind it, which kind of messes up all the plasma and so on in the magnetosphere. Okay, so would a compass be any use? Probably not. So I wouldn't take my compass. It just pointed to the nearest pole. Okay, and then finally Neptune. So this is a bit more exciting. It's got some clouds at least, a bit bigger, and a bit kind of more massive. But roughly, the same kind of rotation rate, 16 hours or so. This one's slightly different in terms of its rotation axis is offset about 28 degrees, so not much more than the Earth's really. But the dipole is offset about 47 degrees. And also, it's not in any way centered towards the center of the planet. It's actually offset by about a half this time. So now what happens here is that the planet spins more or less like the Earth, but now sometimes the magnetic field points, let's say, towards the sun or away from the sun, and then sometimes it's pointing directly up against the ecliptic plane. So that creates a very sort of sickening looking magnetic field when you try to visualize it in 3 dimensions. So again, the magnetic field is a bit stronger than on Earth, maybe just a bit stronger, not much stronger really, so it's quite Earth-like in that sense. And again, it's probably water ice driven dynamo somewhere in the upper part of the planet, we don't know. And again, the magnetosphere extends quite a bit, and this one also leaves a complex magnetosphere, but it's not a corkscrew as such. It's actually more like a sort of sprinkler in terms of like it just drops sort of vortices of plasma as it moves on through the ionosphere. So it sort of breaks things up like sort of a spatter on a kind of sprinkler system in a kind of like a field, if you think about it that way. Okay, I'm going to, well, no, I'll skip it. I was going to try to show you a video, but you can look on YouTube for how Neptune rotates, because there's a couple of YouTube videos give you an idea. I'll just break something by trying to use YouTube at the moment. So yeah, so it's got this very strange kind of rotation which you can Google, and it gets this fairground right. So yeah, you've got to think about it. It points towards the sun sometimes, points away from the sun sometimes, back over and over again. So really quite kind of complicated 3-dimensional change. So again, your compass wouldn't really be very useful on Neptune. It would just point to the nearest magnetic pole, because even though it's got kind of one primary pole, actually it's a very strongly non-dipolar field, which I'll show you next. So yeah, let's just kind of summarizing. So I've just got some maps of the magnetic field kind of drawn as kind of spheres or hammer plots. So it just basically compresses the continents into kind of like a sort of equal area, roughly, plot. So these are what are called the vertical magnetic strengths. So remember the field lines are pointing into the Earth here, so they're negative, so that's why they've been colored blue. They're pointing out at the bottom, so they're colored red. So this is your standard Earth. So yes, you can use a compass, but you will need a correction map that I can provide you with for a very reasonable fee. If you go to Jupiter, you can see that the colors are reversed, but it's quite Earth-like in the sense that it's got a strong south and a kind of bit of a messed up north pole. It's got the spot in the equator as well. So you could use a compass on Jupiter, but I would recommend you take a map. And again, I can provide that at a reasonable cost. If we go to Mercury, you can see that a bit like Earth, it's got a kind of strong north pole with kind of weaker south pole. Doesn't really get very strong at all. So you could use your compass there, although I wouldn't advise using it during a solar storm. If you go to Saturn, it's again like Jupiter in terms of its pointing southward, so it points the opposite way. So your compass would point south, and there's no need for a map. No matter where you go, your compass will always point south. So it's the perfect planet in that sense. Ganymede, I'll put that in there. Yep, perfect moon. Got a bit more structure than, say, Saturn, but still pretty good. Mars is no use because Mars doesn't have a magnetic field at the moment, although it did in the past. So there are some magnetic anomalies still visible. Go to Uranus. No, it's too complicated. Your compass would either point to this large spot or this blue spot, and you'd need a map, and probably wouldn't be very useful. It's just going to point roughly where the nearest strong pole is. And then Neptune as well, even more complicated. You see these various kind of blobs of magnetic fields. So your compass is pointing to the nearest one, and be no good to you at all. So no, way too complicated. Okay, so I'm going to award Saturn the perfect planet for taking your compass with on a trip. It'll work there, no questions asked. Okay, so thanks very much. I'll just summarize. Most planets have or had a field, and they are all completely different, surprisingly. None of them actually look at all like each other. So I'll stop there and I'll say thank you very much.
Oh, thank you very much, Ciaran. I confess I still use a compass when I'm doing serious walking. So your corrections to Ordnance Survey maps are very much appreciated. Well, people are asking their questions. I'll fire off my first question. I was fascinated by the comment you made on Mercury, there are electric fields potentially flowing into the surface. You said, but of course there must also be currents flowing into the surface. There must also be currents flowing out unless Mercury is getting supercharged.
No, they flow in, cut through the core, and then come back out again to space. Yeah, that's what they think. Yeah. Very strange.
Yeah. So right. So okay, so we've got some questions coming in. Let me just right. So the first one I think is Ed Tobias. Do you want to ask? Ed is here. Do you want to ask the question yourself, Ed? Oh, you need to unmute.
Hi there. You said you didn't mind crazy questions, so I thought I would just ask you, even though it really is crazy. You showed us some amazing twisted patterns of sort of magnetic field lines that might be in the South Atlantic area. And I just wondered if we're sort of already heading for a reversal of the magnetic dipole based on that, although I admit it wouldn't be next week.
Yeah, good question. So personally, I think no, we're not heading for a reversal. If you look at the strength of the magnetic fields in the past 150 years, yes, drops like 10%. And it's mainly because that area of the South Atlantic is kind of deepening in terms of its, or weakening in terms of its kind of magnetic strength. But if you look kind of over longer term, and we can look at, say, like lake records or people who've like fired ancient Egyptian bricks and kilns, stuff like that, and you can kind of build up a strength of the magnetic fields going back around about 100,000 years, and you see that actually the magnetic field strength goes up and down all the time, and we've been in a historic high kind of strength for the past few thousand years, and now sort of slowly dropping back to the long-term average. So we're at right about the long-term average at the moment. I mean, that's not to say it couldn't reverse or continue to kind of drop. And if it did, what would happen was the dipole seems to disappear, and you break out like Uranus or Neptune with lots of local spots before it then reappears in the opposite direction. So we think that takes maybe between 1,000 or 10,000 years. It's hard to date old reversals because they're hundreds of thousands of years ago, and the accuracy of the dating technique, the argon dating that they use for lavas and stuff like that, is actually, the error bars are a couple of thousand years anyway. So it's difficult to kind of say precisely, but yeah, you're right. It wouldn't happen next week, unlike some of the movies you might have seen.
Thank you.
Okay, next, Robert has a question. Robert, you're on video, I think.
Why does Mars not have a magnetic field? Why is that? Is it not big enough, not a metallic core?
Yeah, so Mars has an iron core. It's actually got a very thin liquid outer core. But what we think has happened is it's cooled over its lifetime, and the inner core is solidified to the point where you can't get this kind of convective motion anymore. So you don't get the kind of upwelling and downwelling because it's lost too much heat. And also all of the light elements are now kind of at a higher concentration that you don't get much buoyancy. So we think it's because it's a smaller body and it just loses heat quicker. The same thing will probably happen to the Earth in maybe another billion years or so. There's a large debate over how old the inner core of the Earth is. Is it quite young, in which case it's crystallizing very fast and we'll lose our magnetic field sooner? Or is it very old, a few billion years, in which case we'll probably have a magnetic field for a lot longer? The mystery is more why Mercury still has a field when a small body like that should have cooled within a few hundred million years of formation and just basically be solid. So it's not clear why Mercury still has a field. That's the other question. That's the real question.
Okay, thanks, Ciaran. So next up, Julian has a question.
Hi, Ciaran, that was fascinating, thank you. And I had no appreciation that the Earth's outer core was as runny as water. That's quite a thing to get your head around. But my question, did New Horizons discover any magnetic field on Pluto on its flyby, I think in 2015? please?
No. So it's got a magnetometer on it for the solar wind and all that, but no, that it didn't detect anything. Given, I mean, there might be a magnetic field there, but it didn't detect it. So,
Okay.
So at the moment it's an open question, but probably not. I mean, having said that, when Voyager went past some of the Jupiter moons, it didn't detect a magnetic field, although later on we discovered there was a magnetic field. So there could be a very small magnetic field. We just didn't get close enough to detect it.
Okay, thank you.
Okay, next up, Alistair, you had the question.
Yes, thank you, Ciaran. That was a fantastic talk. I really enjoyed it. I will echo Julian's comments. I had no idea the Earth's magnetic field was as best as that, and I'm glad that as astronomers we can find our way with the North Star. But I had a question about Saturn's very uniform and boring magnetic field. Is that in any way, shape, or form the reason for its slight, I don't know if it's hexagon type aurora pattern that it's been seen to have at the poles, or is that some other effect, do you think?
No, I think that hexagonal pattern is the cloud. It's to do with the rotation of the atmosphere. You can make it in a kind of lab. If you rotate it, sort of reasonably large body, you get these patterns forming. I think they just form in generally any spherical body at the pole. You'll get a hexagonal pattern actually, so it's quite a common thing. And I guess the aurora forms sort of similar looking one because they flow in the ionosphere, and that is probably somewhat influenced by the cloud pattern. Well, that's a good question, actually. I don't know, because on the Earth, it's more to do with the conductivity of the ionosphere. That's why the aurora have that kind of generally funny shape. It's to do with like local conductivity patterns. I'm not 100% sure what drives those. There is some atmospheric influence, but because the aurora is kind of 100 kilometers, it's not actually in the general atmosphere of the Earth, it's more in the extended atmosphere. But yeah, good question. I don't think it's to do directly with the magnetic fields of Saturn. It's definitely more to do with the atmosphere.
Okay, thank you.
Okay, next, David has a question.
Hi, Ciaran, and that was a fantastic talk, and definitely one that I'll have to watch again. Stats and figures. And my question is, one theory I've read about Venus, about why Venus didn't develop a magnetic field, was because it didn't suffer a giant impact like the Earth did, and this didn't stir up convective currents. And is this you've seen?
So I mean, there's this theory that the formation of the moon and actually the existence of the moon sort of created a sort of different kind of say chemistry or composition of the Earth in general, and allowed plate tectonics to develop. But I mean, I think it's a bit more complicated than that. I don't know whether the impactor was a key thing. I mean, having said that, Mars also is believed to have had an impactor as well, isn't it? Mm-hmm. Because the one side of the planet is very different looking. The northern half different to the southern half, for example. So maybe for some bodies, an impactor is a good way of kind of kicking the magnetic field into some sort of jump start. But I think the magnetic field of the Earth is a bit more complicated than that, because there's now the original thinking that when it formed, there was a sort of magma layer, called the so-called basal magma layer, above the outer core, which was where the original magnetic field developed before the outer core metal magnetic field developed. Because there's periods of the Earth where there seems to be no magnetic field recorded in the rocks. Now, whether that's a sampling issue or there genuinely was no magnetic field, we're not sure. So it could be that the magnetic field's source has changed over time with the Earth. And every now and then it sort of falls away or fades away and then gets restarted by another geophysical process. I think everyone's still confused as to what the story is about Venus. We still don't know whether it's, why it has one solid lid rather than the Earth whose plate tectonics, or why it's had a runaway greenhouse effect. It's not something I know much about, so I can't really answer that with confidence.
It's been researched as well recently as well, so any evidence of magnetism in old rocks would have been,
eroded, erased.
Thanks, Ciaran. Thank you.
Okay, I think
Thanks.
I think that's all the questions we have so far, except, well, I've got one more. The Earth's magnetic field reverses on quite a long time scale. The Sun's reverses every 11 years. Do any of the other planetary magnetic fields, have we ever seen them reverse their fields?
So on Mars, there are these kind of like stripes like you'd see in the Earth's ocean, which suggests that maybe its magnetic field did reverse in the past when it had one, maybe 4 billion years ago. I mean, it looks like other magnetic fields do vary in time. So Jupiter, for example, so there's no reason why they can't reverse either. Like the Sun, I mean, the Sun reverses every 11 years-ish, kind of on that sort of time scale. So I think just planets, maybe just it's a longer process because what we do is the electric currents to basically, if they're flowing, so to say, clockwise, in order to reverse, they've got to spin counterclockwise or flow counterclockwise, and that flips the magnetic field over. So perhaps it is possible, but it just takes, you know, some kind of chaotic trigger to push them from one system into another system. But yeah, I wouldn't rule it out, and certainly it's, you know, there's no reason why they shouldn't.
Okay, well, thank you very much, Ciaran. I very much enjoyed that talk, and I hope you enjoyed the questions that you got at the end. And so, if everyone could thank Ciaran for a wonderful talk tonight.
Thank you very much for having me.
Thank you. Excellent.
Thank you.
Excellent. Okay, I just noticed there that we were joined also by Stuart Brown, who was John's son. I don't think he's here now. If he's a musician and he's got a band named after a star. Herschel. Margaret, can you remind me the name of the band?
Herschel 36.
Herschel 36, yes, Herschel 36. If you ever get a chance to go and see Herschel 36, I highly recommend it. Very good.
He said he could only drop in tonight because he's getting stuff together for a recording thing tomorrow.
Yeah, no, it was good to see him. So please thank him for attending. Okay, well, thank you, everyone. That's it for tonight.
And before everyone disappears, could I remind members, if they haven't rejoined before the end of December, unfortunately, you will lose your membership. So I expect a flurry of applications to the email address. That would be much appreciated by the Society and the Treasurer. Thank you very much.
Hey, Andrew, can I just say that I know John would have loved that talk tonight and he would have been full of questions. And thanks for the invite.
Oh, yes, you're absolutely right, Margaret. And thank you again for coming.
Okay.
Yeah.
So.